In this module, we're going to continue to look at reactions, only this time we're going to look at oxidation numbers because we're going to need to use that to determine another classification of reactions. So we should first of all define oxidation numbers. And according to Britannica.com, an oxidation number is the total number of electrons that an atom either gains or loses to form a chemical bond with another atom. And from the Purdue University website, an oxidation number is a charge that an atom would have if the compound were composed of ions. I like to think of that definition as a hypothetical relative charge of each atom in a substance. So let's start working from there. Now the thing about oxidation numbers, every atom has an oxidation number. Doesn't matter where it is or what it's in, every atom has an oxidation number. And if we have a compound that has multiple versions of the atom, so there are more than one of a type of atom in there, the oxidation number for that atom has to be the same within the compound. So guidelines for determining oxidation numbers. First thing we want to know is that the sum of the oxidation numbers will equal the charge of whatever it is that we have. If it is neutral, add the oxidation numbers up, you get 0. If it's an ion, you add the oxidation numbers up, you get the charge. So elemental iron has no charge. If we look here, there's only one iron atom, and the whole thing has a charge of 0, so that means that the oxidation number of iron has to be 0. Look at oxygen. Oxygen has no charge, but it's diatomic, so the formula is O2. So the oxidation numbers of each of those oxygens have to be the same. It has to add up to 0, and the only way two things can add up to 0 is if each of them is 0. So that means the oxidation number of oxygen in the elemental form is 0. So from this we can determine that all elements have an oxidation number of 0. We're going to look at ions. The sodium ion has a charge of +1, so its symbol looks like this. There's only one atom and it has a charge of +1. That means its oxidation number has to be +1. We look at an anion the same way. So phosphide has a charge of -3. There's only one phosphorus atom, so the only way the phosphide can have a charge of -3 is if that phosphorus atom has an oxidation number of -3. So from this we can determine that monatomic ions have an oxidation number that is equal to the charge. If we're going to work with compounds or polyatomic ions, we're going to start with the same idea. The sum of oxidation numbers equals to the charge, but we have to use some other guidelines. If our compound has oxygen, the oxidation number of oxygen is -2 unless we have a peroxide. If it's a peroxide, it's -1. If we have hydrogen, and the hydrogen is joined with a metal, or next to a metal, it's going to have an oxidation number of -1. If the hydrogen is with a nonmetal, it has an oxidation number of +1. And if we're dealing with a halogen, so chlorine, fluorine, bromine, or iodine, its oxidation number is going to be -1, unless it's with oxygen, in which case it's going to be whatever it has to be so that the oxygen can have the oxidation number of -2. So let's look at this example of carbon dioxide, CO2. In carbon dioxide, there is one carbon and 2 oxygens in a neutral compound. So we can write an equation for the oxidation number. Sum of oxidation numbers equals charge, so carbon plus 2 oxygen equals 0. We're in a compound with oxygen, so we know that the oxygen has an oxidation number of -2, and we can substitute that into the equation. If we do that, now there is only one variable in the equation. If we solve for C, we're going to see that C has to be +4. So the oxidation number of carbon in carbon dioxide is +4. The oxidation number of oxygen in carbon dioxide is -2. Polyatomic ion, sulfate. There is one sulfur and 4 oxygens in a polyatomic ion with a charge of -2. So the oxidation number equation is going to be the 1 sulfur plus 4 oxygens equal the charge, which is -2. Oxygen in a compound or polyatomic ion has an oxidation of -2, so we can substitute that in. If we solve for sulfur, we'll see that sulfur has to be +6 in order for that to work. So if we +6 on that works. So that means sulfur has an oxidation number of +6. Now, sulfate, the ion, always has to have sulfur with an oxidation number of +6 and oxygen with an oxidation number of -2. It will never change. So if we can remember that, we never need to calculate the oxidation numbers for sulfate again. Okay, we have butane. In this thing, we have a neutral compound that has 4 carbon and 10 hydrogen. So I can put together my oxidation number equation as 4 carbon plus 10 hydrogen equals 0. There are no oxygen, So I go to the hydrogen rule. Hydrogen is with carbon, which is a nonmetal, so its oxidation number is +1. So I can substitute that in. There's only one variable, so I can add the variable, and carbon winds up having an oxidation number of -5/2. So in this case, carbon is -5/2, hydrogen is +1, and we know our oxidation numbers. And it is possible for carbon to have an oxidation number or a fractional oxidation number. Last example, ionic compound, magnesium sulfate. So if we look at this compound, we have 1 magnesium, 1 sulfur, and 4 oxygen in a neutral compound. So that means the equation is going to make magnesium plus sulfur plus 4 oxygen equals 0. Magnesium is a monoatomic ion because it is an ionic compound, and magnesium has a charge of +2, so its oxidation number is +2, so we can substitute that into the equation. Oxygen is in a compound, so its oxidation number has to be -2, so we can plug that into the equation. Now that I'm at this point, there is only one variable, so I can solve this equation for S, and I'll find that S has an oxidation number of +6. Or, I could remember from my previous version with sulfate that it has an oxidation number of +6, and because magnesium sulfate has sulfate, the oxidation number of sulfates has to be the same. Sulfur is +6, oxygen is -2, and sulfate, whenever we encounter it, and magnesium as a monatomic ion has an oxidation number of +1. So these are the guidelines for figuring out the oxidation numbers, and if you follow the rules on the side, you can apply these to any chemical substance that you encounter. This ends the module on oxidation numbers.